I'm going to talk to you today about some work we've been doing in machine learning, both kind of on how we can apply machine learning to sort of pretty significant problems in the world, and then also how we can build computer systems to enable us to tackle larger and larger machine learning challenges. And this is joint work with many, many people at Google. So we're at this kind of interesting transition point. Moore's law has slowed down, so we're not getting the fundamental circuit scaling benefits we've been getting for many, many decades, actually. And we kind of got used to like, oh, computers just get faster, it's awesome. And that's not happening as much anymore. And at the same time, what's happening is we have this amazing new technology for solving problems in completely different ways, sort of kind of the same way that Andre was touching on in his talk. It's a new way where you learn to do things rather than sort of hand coding everything in software. And we want to train really powerful models, really computationally expensive models on very, very large data sets. We want to be able to automatically solve new problems. And then we want to use those models in real products that have very tight computational demands. You might need to serve hundreds of thousands or millions of requests. You have low latency requirements. You have billions of users. So what do we do? Just to give you a sense of the kinds of problems where I think machine learning is going to make a difference. In 2008, the National Academy of Engineering, US National Academy of Engineering, put out this list of 14 grand engineering challenges for the 21st century. And it's a pretty good list. If we solved all these, the world would be a much better place. People would be happier, healthier. The planet would be better cared for. And I actually think machine learning is going to impact how we solve all of these. And in this talk, I'm going to touch very briefly on how it's going to impact some of the things in the red. So let's just start. Restore and improve urban infrastructure. That's one of them. So obviously, autonomous cars are going to be a huge transformative deal for society, right? You'd actually change how you build cities if we had working autonomous cars widely deployed today. Deep learning is incredibly good at going from raw perceptual inputs to high-level understanding of a scene. In order to do that, in order to actually build autonomous cars, you really need to understand what's going on around you from the raw sensor inputs. And deep learning is going to make a really big difference. It's going to have very large data requirements, very low latency requirements, all these kinds of things. Advancing health informatics. I think machine learning for healthcare is going to be one of the most transformative things we can do as a society. Just to give you a couple of examples we've been doing in our group, there's a disease called diabetic retinopathy where there's about 400 million people at risk for this every year. You look at a retinal image like this, and an ophthalmologist can tell you, are you healthy or showing early signs of this disease, or you already have it proliferatively. And it's very important that it get treated, because if it's not treated, you can actually suffer vision loss. But if it's caught in time, you can treat it very, very readily. And so we've done some early work in this space where we now have a machine learning model trained on a fairly large number of retinal images graded by ophthalmologists. And our model is now sort of better or slightly better than the median board-certified ophthalmologist when we published this paper a year ago. We've since done follow-on work where we're now better than retinal specialists at this, which is a sort of higher standard, which is kind of cool. But we're also finding that there's information in these retinal images that ophthalmologists had no idea existed. And so one of the things, this is kind of a happenstance story. So one of the people who was working on this in our group, we had a new person joining the group. And to get familiar with the software sort of setup and how to train models, she said to this new person, oh, why don't you go off and see if you can predict age and gender from the retinal image? Because we had some data with that information available. And the thought was maybe you can predict age within a couple decades, and gender you probably shouldn't be able to predict at all. Maybe the AUC should be 0.5. So off this person went, and they came back a little while later and said, my AUC for gender is 0.7. And they're like, that's interesting. That must be wrong. Why don't you go off and check things? And so they went off, and now they came back, and they said the AUC is 0.85. And so everyone else kind of dove in and said, that does seem correct. And so through that sort of happenstance discovery, we then started looking at what other kinds of things you could predict from retinal images that we didn't know existed. it turns out you can predict a lot of things that are relevant to cardiovascular risk. And so we now actually have a new biomarker from retinal images, whereas previously you'd have to draw blood, do a more invasive procedure to do these kinds of predictions. So that's kind of cool, right? That's something completely novel that we can now do that we didn't used to be able to do through machine learning. We're also pretty excited about how we can use machine learning for healthcare. Essentially, when you're treating a patient, a doctor really wants to know what's the future for the patient, right? And actually, sequential prediction methods for machine learning are actually getting pretty good. We've actually been using them for example, in Google Translate to improve translation. And you can view a medical record as just a long sequence where you only have a little bit of it, and then you want to predict the rest. And so in translation, we've been able to switch from an old phrase-based system, actually the system that Reza was mentioning I worked on code for 10 years ago, to a neural translation system. And this graph is showing you, for a bunch of different language pairs, the quality of the old system as rated by humans in blue, the quality of a new completely learned machine translation system in green, and then the quality of bilingual human-generated translations as judged by other humans in yellow. And you can see we've mostly closed the gap for several of these language pairs through a machine learned system, completely end-to-end learned with deep learning. The new system, so the blue system is about 500,000 lines of code, very complicated, very multiple interacting distributed systems. The green system is 500 lines of TensorFlow code trained on a lot of data. And actually, for some of these language pairs, we have so much data for this that we could only train on 1/6 of the data, just in the time requirements we set for training these models. So we know it can get better if you train on all the data. That's typically a thing that happens in machine learning. So that's pretty promising. So we can take that same technique and apply it to healthcare. So given a big corpus of de-identified medical records, can we predict things about those medical records? Both high-level things like, will the patient be readmitted to the hospital? What are the most likely diagnoses for this patient? What tests should I consider for this patient? You can imagine how this would be incredibly useful for physicians as they're sitting there and you say, well, this diagnosis is 97% likely, but this one is 1% likely. Maybe that doctor themselves has never even thought of this rarer thing. Just to give you a sense, we've since put a paper on arXiv about this task, or this work, a bunch of tasks. And we're pretty excited about this work because here's a representative result from the paper where if you look at the current kinds of baselines people are using for predicting mortality risk, which is really a proxy for how closely do I need to pay attention to this patient right now, that's the dotted line at the bottom. And so you can see we're actually substantially better. Essentially, we get the same accuracy, but we can predict with that accuracy 24 hours earlier. So that really gives you a sense of what patients you need to pay attention to right now and really kind of get the right care decisions made for the most critically ill patients at the right time. A bunch of the grand challenges relate to better understanding of materials in chemistry. So we've been doing a little bit of work in this space where we want to be able to predict various properties of molecules. And the traditional way a quantum chemist does this is they have a molecule configuration. They put it through a very computationally intensive kind of HPC-style simulator called a density functional theory simulator. And in roughly an hour, you get your answer. Does it bind with this thing? What are various properties of this thing, of this molecule and its configuration? It turns out you can use the simulator as a trainer for a neural net. So you now have a supervised training problem where you try to match the behavior of the simulator. But with a neural net, you can actually do it much, much faster. And so essentially, we have a simulator or a neural net that is indistinguishable in accuracy from the much more computationally intensive simulator, but it's 300,000 times faster. And you can imagine that would really change how you would do chemistry, right? You might conceivably evaluate 100 million molecules through this cheap neural net-based predictor and look at the most promising 5,000 of those or 1,000 of those. Reverse engineering the brain is another one. Other people in Google Research have been doing great work on this in collaboration with the Max Planck Institute and other institutions. One of the first things you need to do to reverse engineer the brain probably is to understand the connectivity patterns in the brain. There's a whole field called connectomics, essentially reconstructing the connectivity matrix of the brain. And the way you do this is you take brain tissue, volumes of brain tissue, you slice it very thin, then you do very high resolution electron microscope images of that, as you see in the second picture there. And then from that stack, you try to reconstruct kind of the jumble of connections and neurons in there. And if you prefer a more graph theoretic view, an adjacency matrix. And there's been a lot of progress in this field at Google. This is a graph showing the expected run length in neurons traced, neural tissue traced, before you make an error. And it's important to note it's a log base 10 on the y-axis. Essentially, as you get larger and larger, you can now, with very few errors, reconstruct larger and larger kinds of pieces of real interesting neural tissue, like a whole songbird brain or an entire mouse cortex seems sort of within reach now. And one of the tricks that has happened is through machine learning, of course. And there's a technique called flood filling networks, which essentially use both the raw image data and then the previous sequence of predictions you've made in order to make the next prediction. And so you can kind of bounce back and forth between areas. You basically find the area where the next prediction has the highest confidence. And you can see it kind of tracing out parts where it's very confident. And then when it gets low enough confidence, it will jump off to some other part of the cell in order to trace out the boundary of that cell. And it works in 3D as well, so it kind of traces along one of these pathways until it loses confidence, and then it will go off and jump onto one of the other branches where it's still highly confident. And that works, and you get really nice sort of 3D reconstructions of things like this. And this is a lot of data, so you need a lot of machine learning compute, 600 billion voxels for a songbird brain in terms of the raw electron microscope scans. But it's within reach to now actually reconstruct the brain of a songbird. And one of the broadest and most interesting of the grand challenges was engineering the tools of scientific discovery. And this is where we come to machine learning and systems. So it's pretty clear that machine learning is going to influence a large number of these different challenges. And engineering the right tools for building and training machine learning models for all these different kinds of applications is what we want to do. Our group has now been working on this space of how do we write software systems for expressing machine learning computations in a flexible way for quite some time, about 6 years. This is our second generation system that we open sourced because we wanted to share it with the world and have a community of people work together to improve these tools for lots of different uses that we couldn't even imagine. It's been going reasonably well. So this is a graph of GitHub stars, which is a sort of a measure of interest of how much people are interested in a particular repository on GitHub compared to a bunch of other sort of open source machine learning frameworks. You can see TensorFlow is sort of getting a fairly good sized community and is getting a lot of uses. There's thousands and thousands of other repositories that use TensorFlow to do interesting things on GitHub. As just one example, all the previous examples I showed you were all done using TensorFlow. A person in our group collaborated with Harvard astrophysicists to find planets. So, the Kepler survey had a bunch of data where you want to find planets that transit in front of stars and cause these very subtle drops in the brightness data that you get from that particular part of the sky. And it turns out you can use machine learning to identify those signals. And they found in this data a new planet, actually a couple of new planets, the first known other 8 planets solar system that exists in the universe besides our own that we know about. And it's kind of cool. It's unfortunately 700 degrees there, but years are only 14 days long, so that seems good. Yeah, there it is. Other uses of TensorFlow are kind of really incredibly varied. So there's a company in Amsterdam that essentially builds fitness sensors for cows. They can tell when your cows are sick and can kind of say, oh, this cow in your herd needs particular attention, using a bunch of signals that they gather from this fitness sensor. There are people who are trying to prevent deforestation by detecting very subtle chainsaw noises from like a kilometer away using machine learning. So I think the point is that machine learning is going to be everywhere. It has really widely varied uses that are going to be really important for society. One of the things we want to do is bring machine learning to more and more people. There are actually not that many people in the world who know how to train machine learning models and to apply them to particular problems. The way I like to think about this is there's probably 10,000 organizations in the world that are actually deploying machine learning models and putting them into production use in real products. But there's probably 10 million organizations that have data that should be used for machine learning. And so one of the things we want to be able to do, the way you currently solve machine learning problems is you take data and you have computation, and then you stir in a machine learning expert, which are fairly in short supply, and then you stir it all together and you hopefully come up with a solution. So what if we could turn that into something that looks more like you have data and a lot of computation, but you don't need the machine learning expert to solve a new problem? Right? Can we get the human out of the loop for solving every new problem in machine learning? That would be pretty powerful. So our group has been looking at a bunch of different techniques for this. One of them is called neural architecture search. One of the things a machine learning expert does is they sit down with a particular, for deep learning models, is they say, OK, I'm going to train this structure of model. It's going to have 17 layers and 3x3 convolutions in the first layer. The first layer is going to connect to the second and the third layer, and so on. And they make a bunch of decisions like this based on prior knowledge and other kinds of things that have worked for similar problems. So we're going to use machine learning to do this. We're going to say, we're going to have a model generating model, and we're going to have that model propose model architectures, and we're going to train that via reinforcement learning. And so we essentially propose a bunch of models. We're going to train each of them for a few hours, and we're going to use the loss of these generated models as a reinforcement learning signal. Please steer away from these models, which seem to really not work very well, and towards the part of the space where those models actually seem to work well. So here it is in sort of cartoon form, but you just iterate a lot of times. And eventually you find more and more accurate models that actually solve the problem to quite good accuracy. Here's one of the models they came up with for a smallish image problem, which is pretty interesting. Like a human machine learning expert would probably not wire up a model exactly in that quite so organic a style. But it does show hints of things that have been known to work well in sort of human expert design machine learning vision models. In particular, like the ResNet architecture has these skip connections where you either go to the layer above you or you skip that one. And that's a much more structured style of these kinds of connections that are allowing essentially information to flow much more directly from the input to the output. So that's kind of good. You can look at that and actually get some insights into what kinds of things work well. So it's not like this is not useful for machine learning experts. You can actually look at this and understand what kinds of things this kind of approach is doing. We've then been working on scaling this up to larger problems, including ImageNet. And this graph shows you some interesting things. So one is, on the x-axis, we have the amount of computation required to do inference for a variety of different kinds of machine learning models for ImageNet. And on the y-axis, we have accuracy. And so as you can see, as you apply more compute to the model, models get more computationally expensive, you generally get better accuracy. And there's this kind of frontier of sort of the best models in terms of compute accuracy trade-offs. And it's worth pointing out, every one of these dots here is sort of the output of a significant machine learning research group. Sort of the top machine learning researchers and vision researchers in the world have produced each of these dots over the past 4 or 5 years. So if you look at what happens when you use AutoML, that's better. And essentially, it's better at this high end where you want sort of the highest accuracy possible. It's slightly better accuracy for significantly less compute than the best models up there. And it's better at the low end, where you might want a very lightweight model that runs efficiently on a phone or a flying drone or some low-power device. And so that's kind of cool. This has actually been released as a cloud product for people who have vision problems of their own, but maybe aren't machine learning experts. You can essentially just upload your collection of images, and we will sort of run this kind of computation for you on your problem. And people can then get solutions that are quite high quality for these kinds of problems. So if we're going to apply these kinds of techniques, particularly to very large data sets, we're going to need a lot of computational power. And that's really transforming how we think about building sort of computers for these kinds of machine learning applications. So there's two properties that these computations have that are pretty nice. One is reduced precision is OK. Just like when you're doing kind of very rough back-of-the-envelope calculations in your head, you don't worry about significant figures. You're like, it's 10 times 4. That's about 50. And there's a handful of specific operations that make up every piece of these algorithms. Essentially, if you can do matrix multiplies, vector operations, a handful of specific linear algebra computations, then and do them with reduced precision, that's what you want in a machine learning system. And so this is kind of the second generation hardware accelerator we've built for machine learning computations as a Google designed device for neural net training and inference. If we zoom into one of these chips, one of these chips has 16 gigabytes of high bandwidth memory, quite a lot of memory bandwidth, about 45 teraflops of computation. It has essentially a very large matrix multiply unit. So 128 by 128 array of floating point multipliers, where you essentially can do very high throughput matrix multiplies. And if we go back to the board, the whole board is 180 teraflops of compute with 64 gigs of memory, a lot of memory bandwidth. And it's designed to be connected together because we want more compute for some of these problems than fits on a single board. And so we've wired these up in something we call a pod. And this pod has 64 of those devices, which gives you about 11.5 petaflops of compute and quite a lot of memory for your model. And so that's like the kind of thing we think is going to be applicable for a lot of these machine learning problems. And it's really important that these systems be easy to program. So these models are programmed via TensorFlow. Same program runs with minor modifications on CPUs, GPUs, TPUs. Same program scales via synchronous data parallelism without modification on these pods. So you can start with a single TPU device, scale it up to a 64 device pod, and it all just works without any software modifications. That's kind of what we want. Underneath the covers, we have a compiler that takes a TensorFlow computation graph and then maps that onto, does a bunch of target independent optimizations and then a bunch of target-specific code generation to actually get it to run fast on these different hardware platforms. And so we've now made these devices available externally to people who have their own machine learning problems because we're using them internally for our own, but we also want to make them available to people who have their own machine learning workloads. And so a cloud TPU is a virtual machine with one of these devices attached. You can run TensorFlow on it, and you can essentially run your own computations on it. People seem reasonably happy with it, so a couple of customer quotes in that blog said, that's sort of what we were hoping for these devices is that basically we can improve people's productivity by enabling them to run computations faster and do faster iteration machine learning research, machine learning model development, and so on. There's a wide variety of models that are open sourced with these TPUs, runs all these models. And these are all sort of regression tested to make sure they converge to the right accuracy every night, those kinds of things, which is good. So how are we using them? So we have a bunch of uses for our internal machine learning models. So for example, we can get a 14.2x speed up in the time to converge using a quarter pod versus the old training setup for this ranking model, which was using a bunch of high-end CPU machines. An internal image model with lots and lots of training data used to take 216 hours on the previous setup, now takes 22 hours on a quarter pod. The WaveNet text-to-speech work from DeepMind, we're actually using these for inference in real time for the generating the text, the speech from the desired text. and that generates speech at 20x real time. And our software stack has been improving. So in December, I gave a talk at NIPS where I showed this slide, which was pretty good. In 22 minutes, you can train an ImageNet model on a full pod. In 1,402 minutes, a little less than a day, on a single TPU device, a ResNet 50 model. We have better results today by about 45% roughly, generally improvement. This is the same hardware. So this is just the software stack kind of maturing a bit. And for example, that's an training epoch every 8 seconds on the full pod configuration. You need about 90 epochs to converge. That's what we think interactive machine learning should really be like, is being able to train models at this scale with this kind of interactivity. This was the scaling graph I showed at NIPS in December, using the baseline of the NIPS of the software stack in December. It was pretty good scaling, not quite perfectly linear. Peaked out at about 75,000 images per second on the full pod. Today, our scaling looks better. And it's important to note the y-axis goes up higher, too. So that's 160,000 images a second, or 158,000. And much better scaling through a bunch of software improvements, things like that. The system runs more than just ImageNet. So this is a transformer model, which is used in a lot of sort of language modeling, machine translation, speech tasks. And you see that a single TPU device takes 18 hours. We can train a model with a batch size of 1 million using a full pod in about half an hour and get to the same convergence level. We're making 1,000 of these devices available for researchers who want to do open machine learning research. And you can apply at that URL. Basically, we want people to use these devices and try out these devices for their own machine learning problems. The only requirement is that you openly publish the work that you do. Ideally, we'd like you to open source code for the work that you do associated with this. But we're excited to see what people do with these things. So one question is, what should we build in future machine learning accelerators? And here's the conundrum. This field is moving extremely quickly. So we're producing a growth rate of archive papers that's faster than Moore's law. Like Moore's law, it will probably eventually run out of steam, but not yet. And so it's an incredibly fast-moving field, very hard to keep up with. And if you start an ASIC machine learning accelerator design today, you're going to get your chips back in 2 years after you finish the design and the fabrication process, maybe a year and a half if you're lucky, and it has to remain relevant for 3 years. So how are we going to do that? How can we see the future of machine learning in this incredibly fast-moving field clearly enough to know what we want to be running on these devices 5 years from now? Well, so far, we've taken the approach that we want low-precision linear algebra. That seems to be a good thing to bet on, because most of all the work that I've described so far basically can run in that paradigm. But there's a bunch of interesting things happening that are kind of not quite developed enough to really bet a complete new ASIC design on, but might be things that could inform future ASICs. Some example questions you have here, there's a bunch of explorations on small scales of very low precision training, very low precision inference. Can we get training of 2-bit weights and 2-bit activations to work? That would be a pretty different kind of system than something that's based on floating point numbers, even reduced precision ones. Sparsity and embeddings, how should we handle dynamically routing examples through different parts of the model where every example in a batch wants to go a different direction? How do we handle really large embeddings? If you're training, for example, recommendation models for 1 billion videos, you might want to represent each one of them with a 1,000-dimensional vector. How do you do very random access lookups in these kinds of very large embedding matrices? Should we build machines for very large batch sizes? That seems to be the evidence that that does actually work. And as your problem sizes get bigger, it seems like they're more tolerant of very, very large batch sizes, which is a good sign. If we had to build batch size 1 computation devices, that would be a pretty different design point than the one we've taken. Training algorithms, most things are SGD based. Will second order methods be interesting? One good thing is those seem like they're also linear algebra, so that's maybe okay. But there's lots of open questions. And I think that's kind of an exciting era for computer architecture and really trying a bunch of things. And that experiment is essentially running now with lots and lots of new ML accelerator startups designing different kinds of devices targeted at sort of different subsets of these kinds of workloads. OK, let me switch a bit and talk about machine learning for systems. I think we've done a bunch of work on systems for machine learning, but machine learning really has the chance to really have us rethink how we do fundamental computer systems work. And really, the hypothesis I have is that learning should be used throughout our computing systems. Traditional low-level computing software, operating systems, compilers, storage systems, doesn't really make use of machine learning today. And that should really change. A few examples of this and some opportunities. So here's some work we've been doing in our group for how can we essentially take a large model that we want to run, and instead of running a copy of the model on one device, we want to improve throughput of it by running that model spread across multiple devices, model level parallelism, essentially dividing up the computation so that we now can run a single example through a model spread across many devices and get good throughput. And so for these large models, sometimes they don't fit on a single chip or a single device. And so you actually have to have model parallelism for that. And for other ones, maybe you just want to divide up the computation to improve time to convergence, in addition to data parallelism, where you're sort of doing very large batches split up into smaller batches across many copies of the model. But it's not always obvious how you should apply model parallelism. It's very obvious how you apply data parallelism. You take your model and you make lots of copies of it. But model parallelism is more subtle and more difficult. So here's a model that has a bunch of LSTM layers. This is a translation model. It has an attention layer. It has a softmax layer. Takes in words, A, B, C, D here. Kind of I guess it's the alphabet. And produces translations. And so one way you could spread this across multiple devices is essentially splitting the layers into different GPUs and running that computation in a pipeline fashion across those GPUs. That actually gives you pretty good speed up. So that's a good human-designed heuristic. If the computation is a little imbalanced between each of these layers, though, it's a little unobvious what to do. And so it turns out this is very amenable to reinforcement learning. You can take a graph and a set of devices and make a mapping from that graph, make a model that maps from each of the nodes in the graph to which device it's going to run on, and then measure the step times. And then you can run that in a cycle so that you get better and better at doing placements for this particular model. And you essentially then measure the step time, and that gives you the reward signal for the reinforcement learning algorithm. And so the first bit of work that we did sort of wasn't able to really deal with very large graphs. So we created clusters of nodes that we knew should probably be on the same device. And then we just placed different clusters using this algorithm. So it would take groups of like 50 nodes or something and place those groups of 50 nodes. And that worked pretty well. It actually came up with some pretty interesting placements. So every color here is a different GPU card in the setting that we had. And white is actually the CPU. So in the left-hand thing, which is the translation model I showed you, it decided to interleave some uses of the CPU because it was just sitting there idle, and actually would use that for occasional time steps in the LSTM unrolling. And there's an image model on the right. Both of these got about 19%, 20% faster than the best human-designed model parallelism placements. Since then, we've been working on basically having the model also decide on the clusters of nodes. So taking graphs of 80,000, 90,000 nodes, and then being able to place them by first clustering them and then placing those clusters and doing everything in a differentiable end-to-end way so that we also inform the clustering algorithm as part of the reinforcement learning feedback signal. And that works. It actually does pretty interesting splittings. It can actually split individual per time step computations of an LSTM across multiple devices and gets quite good performance for some of these things. And so 53% better now than the best human placement for 4 4 GPUs. OK, another thing I want to talk about is some work we've been doing on learned index structures. So if you think about the things that are in the core of traditional database systems or sort of data management systems, there are things like B-trees and hash tables and hash maps and Bloom filters, things like that. So it turns out that we started exploring this problem of treating a B-tree. So if you think about a B-tree, it's really an approximate model. You take in a key, and that B-tree will then predict what page of a large storage system that key should reside on, if it resides at all, if it exists at all in this data structure. And so you think of it as giving you a range in which that key must exist, which is essentially a page in a storage system or a database table. So if you take the view that the B-tree is essentially a model taking in a key and predicting a position, then you can actually remove the B-tree and replace that with a neural net. So we now take in a key from our key space, and we try to predict an approximate position. And if we know the set of keys that are present in this thing ahead of time, we can actually bound the error that this model makes for all the keys. And that gives us a range on which we can search. You can think of this as trying to predict the position in the cumulative distribution function of the keys. And the keys can be numbers, they can be like names or whatever kinds of sorted keys you want. But this works pretty well, it turns out. Somewhat surprisingly well. So if you compare it to a B-tree, the top row here, and you compare the two lines down from that, we can come up with a variety of different trade-offs of model size versus computational cost versus the B-tree. So for example, one trade-off we could make is we could get something that's 60% faster than the B-tree, but 1/20th the size. If we prefer the line above, we could get 17% faster and 1/100th the size. So that seems pretty interesting and fundamental for sort of database-style applications. You can also learn the hash function. So one of the things about hash functions is they tend to be designed to work well in all distributions of keys. But that's not really the real world, right? We have keys and distributions of keys that we can observe at runtime. And so if you replace the hash function with a model that learns to map from key to a bucket in a hash structure, you can actually get much more dense packing in these things, leave less space. And so for example, you can get 78% less space usage than a typical hash function for a weblog example, and a bunch of other things like that. Bloom filters are another example where you essentially are oblivious of the key space, and so you do a bunch of hashes and you set bits in this large single-dimensional bit vector, and then you look up those bits. But if you have a model where we take the keys in and we learn to predict what bit to set and what bit to look at, that can give us significant improvements in the space requirement, 36% space improvement over a Bloom filter using the same false positive rate. So that's kind of cool, right? This is really taking machine learning, putting it in the guts of traditional data structures. So where else can we use learning? Lots of places. Computer systems in general are filled with heuristics. Should I insert this thing in the buffer cache? Should I tile the loop this way or that in compilers? And the heuristics really have to be designed to work well in the general case, right? They're sort of oblivious of the exact reference pattern you're using for your particular storage system. They just have to be working well in general. And they can't adapt to how you're using it. So think of all these opportunities for using machine learning in compilers, instruction scheduling, register allocation, loop nest parallelization structures, networking. We have TCP window size growth and shrinking policies, back off for retransmits, what kind of data compression should we use, OSs, which kinds of buffer cache insertion and replacement policies should we use, prefetching, job scheduling, which tasks should we preempt, ASIC design, physical circuit layout, test case selection for ASICs. I think there's tons and tons of opportunities here. Many programs, these are some example flag names from Google, have tons and tons of user-tunable performance parameters. Whenever I'm writing, I'm like, well, I think I know the right value, but I'm not quite sure, so I'm going to make a flag for that. My intern, Russ Cox, years ago, was dismayed at how many flags there were in the Google code base. So he created a screensaver called "There's a flag for that," which would show you a flag for 4 seconds, and then it would show you the description of the flag for 4 seconds. It was relatively amusing what flags we had. And I think we had several 100,000 flags at that time across the code base, not in one binary. But all these things could be tuned automatically, right? Coming up with the right value for how many event manager threads is not something a human should then run manual experiments for and then modify some configuration file that sets that flag appropriately, and then you run it on a different architecture or a later generation server, and that's probably not the right value anymore. We should just learn that. We could just meta-learn everything, right? Placement decisions, how do we do fast kernel implementations for matrix multiplies and 3x3 convolutions, and optimization update rules. We actually have an archive paper on that, where we found pretty interesting update rules that are better than SGD or SGD with momentum or Adagrad or Atom, these kinds of things for many problems. How should we do input preprocessing? There's cropping and random shifting and all these things. Maybe in computer architecture and networking design, we could learn the best design properties. The evidence from neural architecture search is if you have something where you can have a good reward metric, you can actually automatically explore the search space in a way that is very hard for humans to rapidly explore the search space, right? If you run 50 experiments, and now you say, OK, I need to look at the results of those experiments to inform what are the next set of experiments I want to run, that has a human in the loop of every one of those cycles. But if you use reinforcement learning for this, you can essentially run those experiments, automatically incorporate the outcomes of those experiments into the next set of experiments by updating the model that's generating the set of experiments to run. It does mean you need this nice metric of how do you measure and optimize something that you really care about. And having a clean interface to easily integrate this kind of learning system into low-level computer systems is something that I think is an open area, something we're thinking about today. OK, so in conclusion, I left a bunch of time for questions. ML hardware is really at its infancy. It's really exciting time. There's lots and lots of ideas of what kinds of machine learning architectures will make sense for computing hardware, for software that allows you to express ideas efficiently on this hardware. I think we're going to see more and more breakthroughs as we scale the amount of compute that we have to do things like meta-learning on very large-scale problems in all these different domains, the grand challenges domains. Learning in the core of our computer systems will make them more adaptive and more responsive. I think there's lots and lots of opportunities for that. And with that, I will take questions. You can find more info about our work at that URL.
I'm KRS Murthy. Excellent presentation. You covered a lot of areas. Are there areas where the problem is so complex, like the weather prediction, at the global scale, even though different cities, different small adjacent geographies or hamlets are connected to each other by weather? Is it going to be a much bigger problem than we think that ML can solve or not? And similarly, that's one example. And then the stock market, which is a lot more complex than most of the other things that we are solving. And also the next one is failure mode and affection criticality analysis at the large systems level, FMECA. You probably are familiar. Any feedback, comment, any work being done by Google or anyone else?
Sure. So, I think there are definitely interesting problems. I think you alluded to weather. I think weather is an interesting application for machine learning where it's being tried in some small ways, but I think there's a lot more opportunity to do interesting things there. Stock market prediction, that's not my area. There are an increasing number of hedge funds recruiting at NIPS, so I presume machine learning is useful for that, but it's not really my cup of tea. And I think you're alluding to failure analysis and interpretability of these models, right? If they're making decisions, how do we actually know why they're making these decisions? Why, how do we ensure that if we're allowing them to make decisions, we can maybe place boundaries on the scope of decisions they can make to ensure that they operate within safe sort of boundaries that we know they should go between. Yeah, in things that are safety critical, so things like autonomous cars, in medicine, things like that. That's definitely important issues. I didn't really touch on it in this talk, but our group is doing a fair amount of work on interpretability of these models. Yes. So these are definitely valid issues. I didn't cover them in the talk, but they're important. There's some nice work by people in our group on a journal called distill.pub that has some nice analysis of interpretability of machine learning models for computer vision problems, where you can actually understand why is it making predictions in certain ways. Some of the methods we're using for healthcare actually have like attention-based mechanisms. And it's much more important to say for a diagnosis, you don't want the model to say patient needs heart valve replacement. You'd rather the model say patient needs heart valve replacement because this obscure phrase in this medical note from 2 years ago and this test result is a little elevated and this. Right? That's a much more usable system to get humans and machine learning systems interacting in a productive way. Yeah.
Hi, Jeff. First of all, thank you very much for being very open with your research, publishing all the work for us to see, get a glimpse of what great work you guys do in the Google Brain. So, thanks. I just had a question for you with regard to your first area that you showed, the medical informatics. I believe it's very important for the society. It will make our lives better. However, there is this aspect of patient privacy, right? You have to be really careful with what you just said, right? What you tell to the patients, and then how you use this data for your learning. Some people say federated learning on embedded devices may be the way to go. What balance do you strike between obfuscating your data sets and taking the raw data? So your thoughts on that?
Yeah, obviously, I think the potential benefits in healthcare are very large, but as you say, there are very real privacy issues, there's very real regulatory issues, and safety issues. And the medical records work that I showed is all done on de-identified medical records. So that's one thing I want to emphasize. But it's showing, I think, the potential of what could be done in a real healthcare setting. So we're now at the point where we have these good results in de-identified form, but that's not actionable in real healthcare decisions because you actually have to know, it's this patient. And so we're having discussions with different healthcare providers about how can we take this forward, actually build useful tools for them in real clinical settings, but there are definite concerns there. And I think the way I would look at it is the potential benefits of getting millions of medical records that have been made, where decisions have been made by tens of thousands of doctors over decades. You think about that, that's like 200,000 years of doctor wisdom. And distilling that down into models that every doctor can benefit from is, I think, the potential of this approach. So there's definite worries and risks and so on, but the potential is quite large. So we have to figure out as a society what the right way forward is.
Hi, I have 2 quick questions. The first is, has there been an attempt to apply reinforcement learning to user interface design? Because the feedback signals from A/B testing are pretty clear, though perhaps the language of the design space isn't so easy to work with. The second question is, regards modeling the human brain. There's a lot of neurons, but there are animals or creatures like the nematode worm, which only has roughly 300 neurons. And some of the work that Google's been doing in interpretability might be interesting to apply to that kind of system.
Yes, I agree with your second point. I'm not aware of, there's probably some work, but I'm not aware of specifics. I do think understanding the brain is useful as a two-way connection for it. Like neuroscience can inform machine learning. Machine learning things that work well can also inform neuroscience to generate hypotheses. The first question, right?
User interface.
User interface design. Yes, I think that's another area where reinforcement learning could be used. It does seem like as long as you have actionable metrics and a space to explore, that definitely seems like ripe territory to at least try things.
Thanks for your presentation. On the issue of precision, I think I heard you say about you're down to 4 bits or possibly 4 bits for training and activations. So what do you think of the folks? Well, it's there somewhere.
Sorry, I'm just.
You don't have to bring it up.
I'm just going to iconify my chat. Actually, I'll just do that.
So the question is, do you think the spiking neuron guys may be right, and you think that that's where we're headed? That's the question.
Yeah, I don't know. So we're not down. I mean, our TPU hardware is 16-bit floating point computation. The sort of research fringe, not in actual hardware yet, is looking at sort of software evaluation of things like 1 to 4-bit precision. And there's some promising early results there. There's been some IBM work on spiking hardware that is got advantages in terms of very low power usage. It's a little unclear to me if we should actually adopt the spiking. I don't know how to train spiking neural nets is the problem. You essentially integrate spikes over time in order to get sort of more resolution. And it just seems a little indirect, whereas computers can deal with like multiple bits. So that's my opinion, but I'm not an expert on spiking neural nets.
Thanks.
Hi, Jeff. Thanks for sharing your research work. So my first question, I have 2 questions. The first one is related to the AutoML work that has been done. So the question is, so regarding neural architecture search, is it more like doing a grid search on a multidimensional vector space of hyperparameters to find the right set of hyperparameters for an architecture? So have we evolved to do less computationally costly and algorithmic approach towards finding the hyperparameters?
So it's a little bit more than what people typically refer to as hyperparameter search, where you essentially have like some floating point numbers you're trying to find the right values of for things like learning rate or maybe how many neurons I should have in a layer. This actually is a very wide and large search space of possibilities for every layer and how to connect them. And so you have search spaces of 10 to the 40th possibilities. And you're trying to do a combinatorial optimization to find the best settings of the best point in the search space. So a lot of these architecture search things boil down to very large search space combinatorial optimization kinds of problems.
Got it. So we are yet to find an algorithmic approach towards that? Yeah.
I mean, that's what the neural architecture search reinforcement learning-based system does. I do think there are opportunities to make that system much more efficient by like factors of 10 to 100 in computation. But that will then just make us want to run it on bigger problems. So.
Yeah, got it. Yeah, thanks, Jeff. And my second question is, when we train such a large training set, and how do we do the handle the overfitting part of it? And is there any new techniques to tackle overfitting that you have come across during your recent research?
Yeah, I mean, I think overfitting essentially just means you have more generally you have more over-parameterization of your problem and not enough data. But there are lots and lots of problems where we have lots and lots of data. And so overfitting isn't really the problem. It's just being able to actually get a model that is high accuracy in a reasonable amount of time. So yes, overfitting is a problem, and there's lots of things you can do, like things like dropout and so on. Yeah. But for many problems that we actually care about, overfitting isn't the problem. It's just actually being able to train on the amount of data you have.
Got it. So to summarize it, it's more like if you have a lot of data, overfitting isn't much of a problem. Yeah. Okay. Thanks, Jeff.
Hi, thanks for the talk. My question is about bias in machine learning. And with the work that you talked about, like TensorFlow and AutoML, Google has almost democratized machine learning. Anyone can do it. And I know that Google is also trying to be a pioneer in trying to eliminate biases in machine learning models as much as possible. Where do you see Google playing a role in making that more accessible, especially to people who either don't have the resources to be able to tackle that or just don't have the knowledge because they don't come from a machine learning background?
Right. I mean, it's definitely a very real problem. I didn't touch on it in the talk, but anytime you have a machine learning problem, you have the potential for bias to enter the model that you've trained. And the biases can come from the training data that you're using, the fact that maybe you're training on a data set and then testing on a data set with a different distribution. I think it's really important to, first of all, educate everyone using machine learning about these kinds of issues so that they can be cognizant of them, and to really have best practices about how you should go about thinking about testing. Is your model biased? Is it fair for different representatives of different communities? Particularly when sort of it's making judgments that are impactful. You know, I think it's, there are some problems where maybe that bias is not such a huge issue, but there are many where it really is a big issue, and you want to have good practices. So we're continuing to publish work in this area, do research in this area. We will work to inform sort of the non-research community, people who are more machine learning practitioners, about what they should be thinking about and be aware of in these cases.
Do you think there are tools that your team would probably work on in the future that people can use?
Yeah, so for example, our big picture team within the Google Brain team has actually open sourced a bunch of visualization tools that are pretty nice, flexible ways of examining data sets in various ways to look to see if you have bias in your data set or in the models that you've trained. And I think we'll continue to do that.
Okay, thank you.
Yep, thanks.
Yeah, a great talk. So I was very interested when you said that we can now start rethinking how system-level architectures can be designed by just learning what the right architecture should be, for example. Could we take that, do you see this happening in the future, that we're even able to start rethinking how, let's say, the TensorFlow execution happens? So, you know how it's a graph and you just run variables through it, but could that itself be something which can be learned?
Yes.
But
good question. Not yet, but yes. Okay, thank you very much.